In this video, we're going to discuss a quick way to calculate the resonant frequencies for a two-car system by hand. Today in class, we already verified that there are in fact two pairs of complex conjugate eigenvalues for the coefficient matrix in this system. And in our example from class, they turned out to be plus or minus I and plus or minus square root of I. The fact that there are two different frequencies showing up here is also reminiscent of what we saw in our frequency response function from our demonstrations, where we saw that there was kind of a spike in the activity at two different input frequencies. The first input frequency, you'll recall from the video, was a tandem resonance, where the two cars moved together, and the second one was an oppositional resonance, where the two cars butted heads. The idea to getting at these values quicker by hand is to cut out the middleman of converting everything into a first-order system and just look at things as a pure system of second-order equations. This particular trick will only work if gamma equals 0, although on Monday we'll return to this system and look at the more general idea of transfer functions for systems of equations. If gamma is equal to 0, then if we define our solution vector now as just the two-dimensional vector which tracks the positions of our cars, then notice that we can rewrite the left side of our equation above as m1 x1 double prime times m2 x2 double prime. And on the other side, we can factor out x1 and x2, and we're left with coefficients negative k1 plus k2, k2 in the first row, and k2 negative k2 plus k3 in the second row. This matrix right here, which we'll call K, goes by the name of stiffness matrix, because it basically summarizes how stiff all the springs are within our system. So with this new notation in hand, if we assume that the objects have unit mass, in the book section it discusses how to deal with the other situation where they don't. But if they do have unit mass, then the equation on the previous slide reduces to x double prime equals kx. And we can do our usual trick of plugging an exponential function in for x, and then determining conditions on v, the coefficients, and alpha, the exponent, which would make x a solution. Doing so here, on the left-hand side of our equation, results in alpha squared v e to the alpha t, and on the other side would result in k v e the alpha t. After canceling out the exponentials, we note that we get an equation which is very similar to the eigenvalue-eigenvector equation from earlier in this module. The difference here now is that alpha squared is equal to an eigenvalue of k. The conclusion of our calculation on the previous slide is that v times e to the alpha t is a solution to x double prime equals kx if the exponent alpha is the square root of one of the eigenvalues of k. And we'll note and see this in most of the examples, in fact any example of a real stiffness matrix, that the eigenvalues of k often are less than 0, meaning that we're going to end up with imaginary exponents, meaning oscillations, meaning we can calculate resonant frequencies off of those. So let's look at one example before we conclude this video using the stiffness matrix from our MATLAB demo in class. This was the matrix k equals negative 2, 1, 1, negative 2. To find the eigenvalues of k, we simply apply the process we've been using in class and look at the determinant of k minus lambda I. And if you continue down and solve for lambda in this equation, you should get that lambda is negative 3 and negative 1. So to find the resonant frequencies, we're going to look at the square root of these two values. And the square root of negative 3 would actually be plus or minus square root of 3 times I, and plus or minus I, 1 times I, which notice are the four eigenvalues that we saw in MATLAB for the coefficient matrix of the extended system. Once we have these, the resonant frequencies, or at least the resonant angular frequencies, if we're being careful, would just be the coefficients of I here. And that looks awfully lot like a 0, but maybe if I put a 1 and circle it, you'll get the point.